My experiment today involves back titration. Back titration is all about indirect titration. You normally have an anarite that you cannot be able to titrate directly. So first you react it with something else, then you titrate the products that you get. Such kind of a titration, we call it back titration. In my experiment today, I'm going to have this as my anarite, that is copper 2 sulfate solution. I don't know its concentration, and I'm going to determine it. But I don't have any solution here with me that I can be able to use to determine the concentration of this copper 2 sulfate directly. In such a case, we can only use indirect titration, or what we call back titration. And this is how it is going to work. Here I have got iron metal. This metal can react with copper 2 sulfate solution and release iron 2 ions. And I'm going to titrate those iron 2 ions with manganate 7 solution. Then after I get the solution that is going to react, I get the volume of the solution that is going to react with the iron 2 ions. I'm going to work backward and I get the concentration of copper 2 sulfate. And these are the apparatus I need and the solutions. As I have told you, this is potassium manganate 7 solution, whose concentration, its concentration is 0.2 m. This is copper 2 sulfate solution, its concentration I don't know. And this is measuring cylinder. We are going to measure 100 centimeters cubed of copper 2 sulfate solution, and I'm going to put it in this beaker. Then I will react that solution with with iron metal. They are going to react and release iron 2 ions, which I will titrate. The reaction will produce copper metal, and of course there will be excess the reaction will produce copper, and there will be excess iron, and I'm going to filter the two so that I can have a pure solution of iron 2 ions. So I will use the filter paper and a filter funnel to do that. You are welcome. So let us start by the displacement reaction that is supposed to be there between copper 2 sulfate solution. So this is copper 2 sulfate solution. It is blue. The blue solution is, or rather the blue color is due to copper 2 ions. The ions here are going to be removed by iron metal, and iron metal will release iron 2 ions, which we can titrate with manganate 7 solution. So out of this, I'm going to measure 100 centimeters, or rather 100 mils. So this is the solution I have of copper 2 sulfates, and I'm going to react it right now. I'm going to react it with iron metal. It's a displacement reaction. So I put iron metal, and then I'm going to stir for the reaction to take place. We are going to stir. The solution is warm because the reaction is exothermic. It's a displacement reaction. So there we are. The solution is colorless. The brown suspension you see is the suspension of copper powder that is formed inside the beaker. If you look at down there, if you look at the bottom of the beaker, you find a brown solid, brown deposit there. It is copper metal, so the displacement reaction has taken place. And let us now filter the solution. The solution is filtering. What we have inside here is iron 2 ions, and those are the ions we are going to react with manganate 7 solution. So let us wait for the solution to filter so that we can perform the titration. The solution has filtered off, so what I'm going to do is simply I'm going to remove the funnel. Then I put the iron 2 ions into a smaller beaker so that I can pipette 25.0 centimeters cubed of the solution so that I can start the titration. Let me pipette 25.0 centimeters cubed of iron 2 solution that I have made from iron metal. I have 25 mil of my product of the displacement reaction, and the product is iron 2 ions. So I want to start the titration. This solution does not require any indicator. It reacts. It becomes colorless. So we shall. So we will clearly see the end point, the point of equivalence, when it is reached, when the two reacts. So let us start the titration. Let me put manganate 7 into burette so that we can start the titration. My initial burette reading is exactly 10.0 centimeters cubed. Let us titrate, and we see the tighter value that we are going to get when we react the two. Open the tap with the left hand side, then you titrate with the left. We are almost there. Now let's move drop by drop. Oh, we have the purple color. Let us wait to see whether we are supposed to get a permanent purple color. Let's wait for some few seconds. We see whether it is going to change. But it seems that the color is permanent. So we have the end point or the point of equivalence. Let us now take the reading on the burette. The reading is exactly 30 centimeters cubed. Thank you for listening to me. Let us now calculate. Let us start the calculations. We have the titration results, and in the burette we had manganate 7, and we got the final burette reading of 30.0, and the initial burette reading was 10.0. So the tighter value is 20.0 centimeters cubed. In the conical flask, that is the titrant, we had a volume of 25.0 centimeters cubed. We don't know the concentration of iron 2 ions. So, and also the concentration of manganate 7 was 0.02 m. To get the concentration, remember the objective of this titration is to get the concentration of copper 2 sulfate solution. That is concentration of the solution of copper 2 sulfate. That is what we want. But remember, this is a back titration whereby we are going to calculate from the backward until we get all the way to the concentration of copper 2 sulfate. To do this, we need to calculate the number of moles of manganate 7. So let us have moles of manganate 7. Why do we need it? We need it because when we have the moles of manganate 7 and a balanced chemical equation between the two, we can get the moles of iron 2 which have been titrated. So moles of manganate 7, the volume is 20. So we divide by 1,000, multiply by the molarity, which is 0.02, and those are the moles of manganate 7 which we have titrated, and the value is 0.0004 moles. So those are the moles of manganate 7. With the equation, we can know the moles of iron 2 which have been titrated. Let us write the equation, and the equation is iron 2 in solution form meets manganate 7 also in solution form, and it is acidified there. So the products we get here are, we get iron 3 in solution form. Why? Manganate 7 is an oxidizing agent. It oxidizes iron 2 to iron 3. Then itself is reduced to manganese 2 ions and water. So let us balance the equation. We have 5 at iron 2, we multiply 5 at iron 3 on the other side. Then the number of oxygen atoms are 4 on the left, so we multiply by 4 on the right, and hydrogen is 8, so we multiply hydrogen ions by 8 on the left hand side, and the mole ratio between iron 2 and iron 3, the mole ratio between iron 2 and manganate 7 is already shown there in the equation. So we have mole ratio, we can see it is 5:1. Already we have the moles of manganate 7, and you can see from the mole ratio that we are supposed to react 5 times the number of moles of iron 2 to those ones of manganate 7. And already we have those of manganate 7, therefore moles of iron 2 reacted are equal to 5 times those moles of manganate 7, that is 0.004, and what we have now is 0.002 moles of iron 2, and remember these moles were in 25 centimeters cubed of the solution that we pipetted and put in the conical flask. With that, we have done much, because already we have known the amount of iron which has reacted with copper 2. Now with the equation of copper ions with iron metal, we can work backward and get the number of moles of copper ions. So let us have the equation now which produced the iron 2 ions. Remember, we had a solution containing copper ions, that is a solution of copper 2. We reacted with iron metal in solid form. So what we produced was iron 2 ions in solution form and copper metal in solid form. So this is a displacement reaction that happened. Already we know the number of moles of iron 2 which have been produced, and these moles are 0.002 moles. But these moles, remember, they are in 25 centimeters cubed. but our solution was 100 centimeters cubed. So in the whole solution of 100 centimeters cubed that we reacted, the number of moles of iron 2 which were produced was 0.02 multiplied by 4. So these ones become 0.008 moles of iron 2 in the 100 centimeters cubed that we reacted, or rather that were in the beaker that we reacted. So already we have the number of moles of iron 2 produced. We can work backward, and we know the number of moles of copper ions which are supposed to release those number of moles of iron 2. And we can see that the mole ratio from the equation, the mole ratio is equal to 1:1. Therefore, the number of iron 2 ions released is equal to the number of copper ions which were displaced. So moles of copper ions displaced therefore is equal to 0.008 moles. Now we have the number of moles of copper ions displaced. Now, we know these ions were in the solution of copper 2 sulfate, and the copper 2 sulfate solution is, it looks like that. It contains copper ions and sulfate ions, definitely in the ratio of 1:1:1, and therefore the number of moles of copper ions are equivalent to the number of moles of copper 2 sulfate. And in this case, moles of copper 2 sulfate in 100 centimeters cubed were also equal to 0.008 moles, and these were in 100 centimeters cubed. Concentration is quoted based on a liter of solution. So let us work out in 1,000 centimeters cubed how many moles of copper 2 sulfate of such a solution will be there. So we say 100 centimeters cubed of the solution is containing 0.008 moles. Since we quote concentration in moles per liter, so we ask ourselves 1,000 centimeters cubed, how many moles will you find of such a solution? Therefore, this will be 1,000 centimeters cubed over 100 centimeters cubed multiplied by 0.08 moles. So we cancel out. Then we have 0.08 moles per liter or per 1,000 centimeters cubed, which is also written as 0.08 capital M. And that is the concentration of our copper 2 sulfate solution. Thank you for watching my titration. We will have more in the future.